When on-device AI feels sluggish, developers often blame their own code or poor optimization. They assume they are missing a trick in the software layer. But this frustration usually stems from a fundamental architectural mismatch between general-purpose GPUs and modern mobile ASICs. The real issue lies not with your logic, but with how Apple's neural engine handles data differently than any standard graphics chip you have used before. This shift represents a pivotal change from broad GPU acceleration to domain-specific efficiency for on-device large language models. If you do not understand these constraints, you risk building applications that are impossible to run efficiently or suffer catastrophic performance drops when unsupported layers trigger fallbacks to the CPU and GPU. Today, we connect this hardware reality to the engineering trade-offs every practitioner must make when deploying AI locally versus in the cloud. The core of this shift is found in how Apple designed its neural engine, starting with the A11 chip in 2017, evolving through to the latest M5 family. Unlike a graphics processing unit which prioritizes raw peak throughput via massive parallelism at high power costs, the neural engine operates as a fixed function matrix accelerator. It sacrifices flexibility for energy efficiency and latency by executing specific neural network operations like convolutions directly in hardware rather than relying on software emulation. This architectural difference means that weights are baked directly into compiled programs using proprietary compression schemes. The result is a unique on-disk program format that reduces the memory footprint significantly during execution compared to standard GPU drivers. However, this efficiency comes with a steep price for developers who treat mobile chips as miniature desktop GPUs. You cannot simply port a model designed for general-purpose hardware and expect it to run at full speed because the neural engine does not support every operation you might use in your training pipeline. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Accessing this engine is officially restricted through Apple's Core ML framework, which acts as an abstraction layer handling all low-level hardware details. While this provides stability, it introduces significant opacity regarding where specific bottlenecks occur or what optimization opportunities remain hidden from the standard developer interface. This black box nature means that without deep investigation, you cannot see why a model performs well in one version of iOS but fails to launch on another device with similar specs. Recent research has peeled back this curtain through reverse engineering efforts spanning over 302 pages of documentation and analysis. These studies reveal an undocumented direct user space route via private APIs that allows bypassing Core ML for lower-level control. This discovery, often referred to in the context of projects like Orion, demonstrates stable multi-step training previously thought impossible on-device by enabling a system where developers can patch compiled binaries rather than triggering full recompilation loops. The performance gains from this direct approach are staggering. In benchmarks conducted on an M4 Max chip, which powers over 2 billion devices shipping with neural engine technology, these optimized runtimes achieved inference speeds exceeding 170 tokens per second for GPT-2 models. This represents a nearly four-fold improvement overall compared to naive methods and demonstrates the ability to maintain stability over thousands of training steps without numerical errors that typically plague on-device learning tasks. However, relying on this direct access introduces critical risks regarding version fragility. The private APIs used in these experiments are explicitly unsupported by Apple and change frequently with system updates. A patch written for one software release may break entirely in the next, making it a dangerous strategy for production systems where stability is paramount. This creates a stark divide between what is theoretically possible on the hardware versus what is viable for commercial deployment without constant maintenance overhead. The most common pitfall engineers face is the so-called fallback trap. Not every layer of a neural network maps cleanly to neural engine-supported operations. If your model contains even a single unsupported operation, execution falls back to the CPU or GPU. This transition negates all speed benefits and causes performance spikes due to data movement overheads between different memory pools within the chip architecture. This fallback mechanism explains why optimization often feels like magic or luck without architectural context. A developer might spend weeks refining code only to find that a single obscure layer in their model is forcing the entire system into a slow mode, killing battery life and destroying latency expectations. The cost of this unsupported operation is not just slowness. It is a complete loss of the efficiency gains that make on-device AI viable in the first place. For production stability, Core ML remains the recommended interface despite its opacity because it guarantees compatibility across device generations without requiring constant code rewrites for every OS update. However, for cutting-edge optimization tasks like fine-tuning or specialized inference where maximum performance is required, knowing how to leverage direct hardware access allows practitioners to unlock tiers of speed unavailable through standard frameworks. The decision framework you must adopt shifts your judgment from asking if a model is fast enough in isolation to verifying that every single layer maps to neural engine-supported operations. You need to treat the hardware constraints as hard boundaries rather than soft limits that can be smoothed over with better code. Understanding these architectural realities dictates where you deploy models locally versus in the cloud, ensuring that your engineering judgment aligns with the physical capabilities of the silicon powering your application. The gap between what a GPU does and what this dedicated ASIC enables defines the future of on-device intelligence. By recognizing that efficiency comes from baking weights into fixed functions rather than general parallelism, you can avoid the costly mistakes of trying to force software solutions onto hardware designed for something entirely different. The path forward requires respecting these architectural differences while leveraging new reverse-engineered tools where the risk is acceptable and the performance payoff justifies the maintenance burden. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.